This is the demonstration, SAS demonstration of lecture number 10. All right, so I'll only do the data example for the dengue fever virus infection example. So here's the SAS code. The code already posted on Canvas, so you can download from there. The first step is to set up a library, which you can refer a specific library for lecture 10 and link that to the data on your local computer. All right, so here's the code on my computer. Then after you set up this link, so I can see the data under the folder called lecture, Lec 10. I have a bunch of data set right here. So this is the data I'm going to use. All right, so this is the data with a binary outcome measures, which is the dengue fever. So this is not a regular setup. So here 2 means no infection. And 1 means infection, and also have the ID number, so it's unique for each individual, the age for each individual, and also this MOSNET is the indicator, binary indicator, 0 and 1, indicating if the individual used the mosquito net. And the last one, sector, is the geographic location of each individual in the study. All right, so the first one we did is the logistic regression model that set up the specify the mosquito netting as the binary data set or categorical data set with a reference group equal to 0. So without setup reference equal to 0, SAS will automatically use the largest number as the reference group. And then sector reference equal to 5. So without set ref equal to 5, SAS will still use 5 because that's by default. And in the model statement, we set up the regression model. So this dengue D and GUE is the binary indicator. But remember, this is not a 0 and 1 data. It's 1 and 2. So we have to specify the event equal to 1. And on the right-hand side of the equal sign or the predictor variables or independent variables. So that includes age, which is a continuous variable, and the mosquito net using, which is a binary, and 0, which is no use of mosquito net, is a reference group. In the sector, we use section location number 5 as a reference. So they'll automatically create the 4 dummy variables for sector 1, 2, 3, and 4. All right, so we can run this model. Looks like there's some little error right there. Okay, I think we need to change this to Lec 10 dot fever. Okay, the reason is keep the previous data resource, because now we have a new folder, a new library called lecture 10, and we put the data within that folder. So we have to we refer the folder to get the data sets. Otherwise, SAS cannot see the data set. All right, just make sure there's no problem. We can rerun it. Okay, and once we run this model, so we have like the procedure, logistic procedure give a multiple output, a bunch of tables. The first table is the basic information, the data set you use, the response variable we use, which is the dung variable, and the number of response levels. We have 1 and 2. We specify 1 as the infection or case, and the model type, which is the logistic model for binary data. And then let's give the basic information like the number of observations, which is the sample size in your data. It's 196. And also it tell you 57 among these 196 individuals get infection, which is got number 1, which would lead to 139 and infected individuals. And also it give you the categorical variable setup for the mosquito net using, because it's a 0 and 1 data, you just have 2 levels. But for the sector, because you have 5 different levels, it created 4 domain variables for 1, 2, 3, and 4. And if all of these domain variables equal to 0 simultaneously, will indicate the individuals from sector number 5, because number 5 is a reference. And also, if you still remember in the lecture, I talked about this basic model fit statistics. We have AIC, SC, and negative 2 times of the log likelihood. Remember the AIC and SC also use the negative 2 times of the log likelihood, but the plus, it penalized terms. And therefore you see the AIC and SC have a bigger value than the negative 2 times of the log likelihood, what we call deviance. Here is not meaningful to compare between this individual criteria, because it's not meaningful to interpret the value itself. The only meaningful way is you use AIC consistently for multiple models, for model comparisons. But what you can remember is this value is always greater than the deviance, negative 2 times of the log likelihood. And also the smaller number of AIC and the smaller number of SC is better. We always want to see the smallest number. That's the best model. All right, and the next one is the task for the entire model with the 6 degree of freedoms, 1 degree of freedom for age, 1 degree of freedom for mosquito net using, and 4 degree of freedom for the geographic location. So this is a task for the entire model. We call it overall test. There's give you 3 different type of tests: likelihood ratio, score test, and war test. But the things in common is they are all chi-square based tests, because the asymptotic distribution or chi-square distribution. Here's the p-value based on the test statistics, the chi-square value. But at 0.05 level can give you the same conclusion, which indicate the model you just run is statistically significantly better than the no model. All right, and the next one is similar to, we call it ANOVA type of test. It will test each effect, not each individual parameter, but each effect, because here we have 3 different effects: 1 of age, 1 of mosquito net using, 1 of the geographic location, which is a sector. But the sector have actually 5 different levels or 4 degree of freedoms. And this test is testing each individual effect as a whole. It won't test each parameter. The next table will test each parameter. All right, and you can see there, age have a significant p-value. Again, this is also a war test. A war test is a kind of chi-square test, because the asymptotic distribution is chi-square distribution. And we reject null hypothesis for age and believe age is a significant effect to the dengue fever infection. But mosquito net using is not, because it got the p-value 0.79, and the geographic location as a whole is a significant factor. So remember, the null hypothesis for testing the sector is that all the sectors simultaneously have the same odds or same risk of getting infection. So that's the null hypothesis. So you test this 5 parameters simultaneously, or 5 the risk for the 5 locations at the same time. So we have 4 degree of freedom, 5 minus 1 degree of freedom, and they reject null hypothesis. This is not an individual test of each individual location with a reference, but this is just test as a whole. So the next one is we call the analysis of maximum likelihood estimates. So this is actually give you the estimated parameter and also do an individual test for each of the parameters. The difference between this and this is it will treat the sector as a 4 degree of freedom and at least each parameter of the 4 dominant variables individually. And therefore, you can see the task for age is the same as the task here, and the task for the mosquito net using is the same as here because they are all 1 degree of freedom. The difference is for the sector. And now they're going to have a 5 different levels, and if we choose sector number 5 as reference group, and there's going to be 4 dominant variables for comparison of each individual sector 1, 2, 3, 4 with the reference sector sector 5, and the resultant estimate was the beta estimate for that specific dominant variable. And also they do a individual test. This is still a word test, chi-square, asymptotic chi-square distribution, a word test, and get a p-value from that chi-square test. So for example, sector 1 is statistically significantly different from sector 5 in terms of the risk of infection, because the p-value is 0.03. But sector 2 and 5, if you do that comparison, there's no statistical difference, significantly different effect for that comparison. Similar, if you compare 3 and 4, 3 and 5, 4 and 5, there's no significant difference. So only the comparison between sector 1 and sector 5 are different. So this is why I think in this test, in the test of the whole sector effect, the null hypothesis is that simultaneously equal, and the alternative hypothesis is at least 1 pair are not the same. But remember, here is not the exhaustive number of pairwise comparisons. They only compare level 5 or sector 5 with other things, but you can still choose one of these factors as a reference and do a comparison. Because we have 5 different levels, the exhaustive number of pairwise comparison is 5 choose 2, which is 5 times 4 divided by 2 times 1, which is 10. So in other words, you should do a total of 10 tests to know how many pairwise comparison get the statistical statistically different difference, statistically significant difference. All right, so that's the table for the analysis of maximum likelihood estimate. And again, you not only do the test, but you can still have the parameter estimate. And this parameter is all the beta parameters. So this is beta 0, beta 1, beta 2, beta 3, beta 5, beta 4, etc. So once you have all this estimate, you actually can build up, or you can write specifically express your model, because your model will have the 7 parameters from beta 0 to beta 7, because we have 6 parameters for this predictor variables and 1 for the intercept. So you can plug in this number, and then you get the model set up. And the other thing is, remember, this estimate is not the odds ratio. It's the log of the odds ratio. It is still on the linear scale. It's not on exponential scale. So if you want to interpret the effect in terms of odds ratio, you need to look at the table after that. So again, this is actually a repeat of the effect from the above table, but it removed the intercept because the intercept is a nuisance parameter. We're not interested in interpretation of that. beta parameter. But here we have the age odds ratio, and because age is a continuous variable, and therefore this odds ratio is interpreted as the ratio of odds of being infected of dengue fever, whereas comparing the two hypothetical population with 1 unit different in age. So it's basically just 1 year different in age. Like say, if you have a two hypothetical individual whose age are different by 1 year, and this will be the odds ratio for them to get the infection, assuming all the other covariates are the same. The net using status or the geographic location are the same for these two individuals. Okay, so that's interpretation for age, and age is the only continuous variable in this model. And the mosquito net using 1 versus 0. So this is the odds ratio to compare rows use the mosquito net versus not use, because it's 1 versus 0. And the value greater than 1 means if you use the mosquito net, which is the 1 in that status, so you will have higher odds of being infected. And is about 39.6% higher. So which is this number minus 1 is the percent increase in odds. All right, and similarly, we can interpret the geographic location, 1 versus 5, 2 versus 5, 3 versus 5, etc. So all this odds ratio, it is the comparison between each individual sector with the reference sector 5. So for example, the first comparison between N1 and 5. So if you are in geographic location sector 1, so your odds of being infections only 11% of rows in the location sector number 5. So that's the interpretation of these odds ratios. All right, beyond this point estimates of the odds ratio, we also have 95% confidence limits, basically just 95% confidence interval based on the word test. So this will basically give you the same information as the p-values. So you can evaluate this way. So if the interval includes a 1 within the interval, and that means this is not a significant effect. So for example, the comparison between sector 2 and 5, 3 and 5, and 4 and 5, they all include a 1, and that means these effects are not significant. But for the other 3, you can see this doesn't include 1 in there, and this doesn't include 1 in there. So they are not, they're statistically significant. And also the mosquito net using is not significant. You can see 1 is within the 95% confidence interval. All right. So this is all the output from the logistic regression model. So it's a typical output. So if you run any prog logistic, you will have something like that, unless you're asking something else. So for example, right. So for example, the next one, so this is not going to be the one we're going to use here. All right. So the next one, we ask for the lack of fit test, right? So again, we basically just repeat a model, but the one more thing we're asking is the test for the lack of fit. So if we run this, so basically you got a very similar results from the previous procedure because we basically just repeat them. But at the end, you can see we have these lack of fit test called the Hausmer-Lamachel goodness of fit test. And this is an 80-degree of freedom test, so which means it tests the model itself to see if the model lack of goodness of fit. But this reject null hypothesis means So reject null hypothesis here for this AD broad freedom test means there's no evidence to say the current model is not sufficient. So basically, in other words, it's sufficient to use the current model. All right. The next one, we actually, so if you still remember that, this is if we want to look at the n-adjusted age effect, we can rerun a logistic model with age as the only predictor variable. We don't have to worry about the adjustment for mosquito net using and for the sector. So if we rerun that, we see the odds ratio is 1.029 versus the adjusted odds ratio with 1.025. So here we can evaluate, if you want to evaluate the confounding effects, you can do similar thing, but here is not a good way because we want to evaluate the confounder individually. But here you actually add two confounder variable together. One is the mosquito, the other is the sector. But if you want to evaluate individually, so you can run this n-adjusted odds ratio, then you run another model with age as exposure and one of the other possible confounding variables. And you see if adding that specific variable will make the odds ratio for age change more than 10%. So if there's more than 10% change, and you can use a rule of thumb and claim that a variable being added is a confounder or is a confounding variable. All right. But here, you can see n-adjusted odds ratio is 1.03, about 1.03. But if you adjust for both mosquito net using and for the geographic location, it's 1.025. You see, it's a tiny little change for the age effect. All right, the next one is the one we want to get a plot. So this is the plot of each individual probability of infection versus the individual. So basically, versus the individual predictor variable. So the first thing is we need to rerun this model, but instead of just that SAS will output these tables or the testing results, we also ask SAS to output a data set called outdone, and also with the probability. And then after that, we can either make a plot, or we can let SAS to output to print out this specific data set. But here we really just print out. And in this one, as SAS running the regression model, it also gives you the plot for the effect. And the plot for the effect is the resultant probability versus the predictor variable. Okay, so the things before that are all the same as the previous output, but just at the end we have this figure called predicted probability for dong equal to 1, so which is just the risk of being infected, because dong equal to 1 is the infection. All right, so this is the probability versus age as one of the predictor variable, because the SAS will use this as the X variable because this is continuous. So you always get a better curve, more smooth curve if you plot this versus a continuous variable. And because we also have other two categorical variables. The way SAS do that is we subdivide this into 10 different subgroups. And the subgroups is determined by the combination of the net using status and also geographic location. So we have a 0, 1, 0, 2, 0, 5, and 1, 1, 1, 2, all the way to 1, 5. Each line is differentiated by a different color. Like say, I would not say this, sometimes this color are similar, like this green and this green. But I mean, you still be able to differentiate them because they are not huge number of subgroups. Because then if you have a huge number of subgroups, you probably cannot just use the color. You might use color plus a symbol plus a line type to differentiate among them. But the figure will becomes too noisy that way. And here basically I just give one example. So for example, if we want to look at those with mosquito use, and in geographic sector number 3, so we need to look at this about, is I would say purple, like the purple. It's not the perfectly purple, so this is a perfect purple. It's similar to purple, but not like this, not like brighter like this one. So you need to find a line like that, and that is the line for this specific group. So I would say this is a line here. So that's the line with the highest risk of being infection compared with others. The reason is, looks like geographic number 3 is the highest risk. And also the net using will give you a higher risk than the non-mosquito using groups. And therefore you can see this is the group right there. And also this gives you the change of infection, of the probability or risk of infection over age. So if you're really over 40 years or over 60 years, you have very, very high estimated probability of being infected. Like say if you're 80 years old, your chance is almost 70, I would say 76 or 70, it's about 76%, a little bit more than 75% of being infected, which is the prediction by running this logistic regression model. All right. And the next one is if you want to look at each individual's probability of infection, so you can say list, but one caveat is before print this, you need to keep in mind this be a long list because you have 196 individuals. But in case you have a huge data set, like say 10,000 individuals, don't do that. So this is just a caveat. All right. And here, because it's not too bad, it's around 200 subjects. So we can still do this. So you can see, so we give you the observations from 1 to 196. And for each individual, I'll give you, again, this is just a repeat of the data. So you have age, you have ID number, age, mosquito using status, the dengue fever status, which is the outcome status. So this is no non-infection for this individual, and the location. And also at the end, you see there's a probability. So the 0.03 is just the probability of being infected by dengue fever virus for the individual with this demographic feature or risk factor. Like say a typical people with like 16 years old use the mosquito net and in the geographic location sector 1 will have 3.23% of risk of infection. So similar to that, you can do interpretation for every single subject because they all have a different age and different location and different mosquito using. But it might possible you can have some pair of individuals which have exactly the same value for these 3 predictor variables. All right. So the last one is very important. It is that we want to evaluate the predictive accuracy of the logistic regression model, because after you run a logistic regression model, you always have the predictive probability. This is based on the model fitting. And we want to evaluate this predictive probability can give you an accurate prediction for infection of diphtheria virus in the future. And the way we do this is we run the model again, but as we run this, we need to specify we want logistic regression procedure to output the ROC curve. So that is specified in the prog logistic statement, not in the model statement, remember. It's just in that title statement. So it's nothing changed for other statements, nothing changed for model, nothing changed for class. So you just rerun this, but first you need to open the figure, and then at the end you close the graphic function. And again, everything before that, it will be the same as you got previously. Right here, what you get is the ROC curve. So as I said, the most important metric or benchmark we need to use is area curve. So in this case, it's 0.7368. So basically means 73.68%, about 74% accuracy. So this will be interpreted as the overall accuracy of the model to predict of the probability output by the logistic regression model to predict the diphtheria virus infection. So if you do that, so that's 74%. All right. So that's all for the SAS demonstration, and I hope you can look at this video combined with the previous 2 videos of lecture number 10, and combine them together, and you can have a better understanding. All right, that's all for lecture number 10.